So your main first module, your basic is that it is a Internet of Things is that you're communicating uh, things to enhance people's lives. So what you're doing this is you're doing this online. Um, so this Internet of Things, the main goal is to connect the unconnected, and then you have in IoT you have sensors that control the physical world. Your physical devices and controllers for efficiency and accuracy, automation, and enablement of advanced application. So you have a question called Genesis of IoT. So first, IoT was founded by Kevin Ashton. So what happens here is you have a business and social impact, and then you have intelligent connection. So you have connectivity, network economy, and immersive experience. Then you have IoT in the end. These are the four phases if they ask. So okay, in connectivity, what happens is you're digitalizing the access. That is via email, web browser, search. Everything is made online. So network economy. That is you have your business, digital businesses which are present. That is your digital supply chain, collaboration, e-commerce websites. Immersive experience is to give digital interactions, that is via social media, mobile application, cloud, video, audios. And then you have IoT. These are this is the digitalized world where people, processes, and data, all of these have been digitalized. So IoT and digitalization. IoT connects things to the internet. So this is called Internet of Things. So the things and you use things and Wi-Fi devices. It can be classified as things, operations, and advantages, under which you get Wi-Fi devices. Things are Wi-Fi devices. Operation of a Wi-Fi device is to track. You give any example. Track the different parts of like you're tracking the person through the mall, and then your main advantage is that your product. You know for product and security reasons, how long the person was there in the place. Digitization is converting information into digital format, that is things with data and business events. So digitization of photographs. So what you did is things is first you bought in a digital camera, and then advantages is no film required, so you have better battery life, better pictures. You have a question called M2M architecture. Here there are mainly three layers. There is application layer, service layer, and network layer. In application layer, you have automotive application, home application, and then energy application. And then common service layer, you have common service layer, communications, technology, and protocols, common network, and then connected devices and hardware, communication devices and hardware. And network layer is like connecting them to devices. What happens here is in service layer, you have a service application platform. Here the challenge is designing the IoT architecture in heterogeneity of devices, software, and access methods. So these are horizontal and allow interoperability at all levels. So these are mainly horizontal and allow interoperability at all levels. You have RESTful API that allows LoRaWAN system to manage one of the IoT networks. This promotes end-to-end IoT communication. Here, application layer, smart energy, assets, and asset tracking, and then fleet management. And then you have in service layer, you have these are horizontal layers, and then they support management, and then RESTful APIs. Here, network layer, your application takes an API and connects it with the sensors. That's what you have explained over here. Application layer is the protocol standardize the API's definitions. So application is making it interactable for business intelligence systems, and then industry specific for its own data. Then server level, here you have physical layers that apps run on, and then your APIs and middleware supporting the third party apps. And then for network layer, you have communications in wireless mesh point to point topologies, and then you have device domain gateways. You have device domains and gateways which are present. IoT impact. So first you draw a graph of number of devices being used. This is the world population. First it was like one person. If out of 10 people, one of them had a phone. Then it became every person had one phone by 2008 or 2010, and then they went on increasing. Now it is almost up to five phones or devices per five things per person. Then it has gone up to 50 billion objects. So you have IoT challenges, that is your BIPs. Okay, you have BIP square. Okay, what happens here is big data and analysis. These ensure that there are large challenges. You have large number of sensors, you need to collect all these data, and then all these data must be stored in a place, so that becomes a problem. Interoperability, that is standardization of architecture and protocols. So if you have many different types of sensors and different types of protocols being used, it should be made that it should be interoperable, so I can use one protocol layer to function or run the other. If it is run only by one specific protocol, then it will become hard to manage. Then you have privacy, that is your individual data is being shared to IoT devices, which continuously collect your real-time information, which becomes a problem. So your privacy is at stake. Your scalability. So that is since you have a lot of devices, large number of sensors being present. When you scale, there is you need to cover a large number of devices under the challenges. So for every large scale of development that is done, you need to provide an equal level of IP addresses. You need to be, your allocation of resources must be done by planning them out. And then security, you have security threats, and then securing IoT is a major level task. IT and OT main differences. So you have operational focus, priorities, types of data, security, implication of failure, network upgrades, and then security vulnerability. So what happens here is in operational focus, this is done using business operations, which happen 24/7. Here manages data, computers, and communications in a secure way. Your priority is main, it should be available, then integrated, and then secure. Here what you're doing is your security is your main priority, because all your data is on the internet, then integrity, then availability. Then you have types of data, that is you have monitoring, control, and supervising the data. Here your data is in forms of voice, video, transaction, and bulk data. Here security is controlled by physical access to devices. Your devices and user authentication are authenticated to the network, that is all your data is present on the web. Implication of failure. OT, if OT is disrupted, then the whole business, it impacts the business. This business impact can be minimized. Okay, so what you do is when the workers aren't around, so after the work hours, what you do is you try to repair the failure. So network, this operation maintenance, you have only during operational maintenance window can be done. Here you have outage, and when workers are not on site, it can risks and network upgrades can be done. Your security is it is low security, and then you're using proprietary protocols, that is your common protocols. Here's high security, so your patching of hosts is required, so you need to make sure your hosts are secure. Then your internet is required vigilant protection. So you have IoT World Forum, that is IoT WF, that is based on technologies like IEEE 802.15.4 and wireless point-to-point multi-point systems such as 801.11. Okay, these also include wired devices also. So what happens here is you have mainly 7 layers. You have a center and you have an edge. Edge is where your actuators and devices are present, and your center is where your data is transmitted or being used. Okay, so you start from below. You have physical devices and controllers, that is things of IoT. Second one is connectivity, that is your communication devices and processing unit. Edge computing, data analysis and transformation. Step 4, data accumulation, that is what you're doing is storage. Data abstraction, aggregation, that is you're dividing and accessing the data accordingly. So here data analysis and transformation. Data accumulation, for edge computing you have analysis and transformation. For data accumulation is storage. Data abstraction is aggregation and access. Then application is reporting, analyzing, and control. And then your collection and collection and processes that involves business people and business processes. Okay, so these are your world forum levels. So what happens here is, in first one, your endpoint devices generate data. Your second stage, that is your connectivity, they transmit data through network elements like hubs, routers, switches. And then you have third one, that is data edge computing, that is your data redundancy and information processing, it happens over there. Fourth one, accumulation, that is it stores the data into databases. And then fifth one is aggregation and access. So you're abstracting the formats, you're sending it in the required format, and then you're dividing the data. Sixth one is your application. Your application is where your software is monitored and controlled. Then seventh one is processing, collection and processing. So what happens here is, you're sharing the app information and collecting the information of IoT. Then you have access technologies. So draw this diagram. You have EMV. You have your NFC tags and all. So all this comes under your EMV, that is under your electromagnetic waves. And then less than 10 centimeters, you have WPAN, that is WPAN, FAN, WAN, HAN, NAN. And then if it is greater than 5 kilometers, then you have WWAN, LP WAN, that is wireless. And then you have cellular, that is licensed. And then LP WAN, that is your unlicensed. This comes under 100 kilometers. You have point-to-point and point-to-multi-point access. Your PAN is your personal area network, that is within your home area space. HAN is home area network, that is within few meters inside your home. It is not just related to one place. You can move around your house and still have. This includes Zigbee and Bluetooth low energy. Then you have NAN, that is your neighborhood area network. So it is like, okay, here they've given clear formats. Wireless personal area network, wireless home area network, wireless field area network, wireless local area network, wireless neighborhood area network, wireless wide area network. Wide area network comes off under your less than 100. And then you have low power wide area network. So these point-to-point topologies, what happens is, you have one point and then it connects to another point. So you have only single object that can communicate with a single gateway. However, this point-to-point, when objects are established with individual sessions, the point-to-point gateway in this case refers to more physical sessions. So it is from one device to another device, that's all. In multi-point topology, what happens is, the topologies allow the point to communicate with other than one point. So you have many points which can communicate with each other. So for example, sensors with both collection and forwarding functions can be used, while some other nodes collect the smart data, sometimes instruct the sensors to perform specific operations. So you can detect and perform specific operations. So what happens here is, you have star topology. In the star topology, only one can connect to another device, and then it can give you instruction only through that. And then clustered stars is, you have fully functional devices and reduced functional devices which are present. So point to multi-point technologies allow one node to have more than one path, and allow the node to form a mesh topology. This redundancy means that each node can communicate with more than just one node, and gives an extended. These two. This is written as mesh topology. IoT management and computing stack. Here, managing the data which is being generated in large amounts. So the smart meter generates data and then it's uploaded to the cloud. Requirements: having minimum latency, conserving network bandwidth, and then increasing local efficiency. What you're doing is minimizing latency, is analyzing the data is closer to the device, closer to the edge, so that it collects the data and then stops the disasters from averting disasters from occurring. In conserving network bandwidth, it is not necessary that all the data is converted all your thousands of data is converted and then uploaded to the cloud. So you just minimize whichever is required, and then you make sure you're conserving your network bandwidth, and then increasing local efficiency. You don't have to, when you're collecting and securing data all over the world, so you have a wide geographical area to be covered. So when you divide it into smaller parts, you can increase local efficiency little by little. So this is your IoT traditional cloud structure. You have endpoints, you have core network, and then you have data center or clouds. So what you're doing here is you have bandwidths in the last mile. That is IoT network, that is limited. When dealing with thousands and millions of devices available, the bandwidth may not be in orders of tens of kbps. See, bandwidth to last mile IoT is very limited. You have latency which is very high. And then you have network backhaul from the gateway, which can be unreliable data through the satellite links. Then you have volume of data being transmitted is very high. Then you have big data is getting bigger. So then you have fog computing. The solutions of these challenges mentioned is that the best known is fog. Edge service in edge service, the best one is fog technologies. Fog computing, and then any devices with the computing and storage can be done in fog mode. So in fog, what you have is you have a smart object, you have fog layer, IPv6 core IPv6 network, and then cloud storage. What happens here is your data is being sensed, controlled, and computed. Okay, so you have millions of embedded systems with low power bandwidth, and then tens and hundreds of multi-service layer edges, and then 1,000 backhauls and gateways, and then transaction response time from core network to data center, and then you have hundreds of data centers. So these cloud services are very close to the edge surface and near the IoT endpoints. The fog nodes has contextual awareness of the sensors, and it's managed because of its geographical proximity. The fog mode is able to analyze information from all sensors and can provide context for message receiving, and may decide to send back only relevant information. So there are characteristics of fog computing: contextual location awareness and low latency, geographical distribution, deployed near endpoints, wireless communication between fog and endpoints because it is near the endpoints, and wireless access can be easily achieved, and then used in real-time interaction. You have edge computing. In edge computing, what happens is when fog node is sitting near the electrical pole, the distribution of network may have an excellent view. But what you need is fog mode would give you a wider view of whether the problem was just localized or affecting the entire area. Edge computing is able to communicate with each other by sharing information on small subsets. That is your electrical distribution grid, and then your monitorized local power quality. You get minute data which is present by edge.